Hello and welcome to the Tech Innovador podcast presented to you by IEEE Tech West Sri Lanka. Tech Innovador is our podcast series which we discuss various current technologies and explore their uses and advancement with industry experts. I am Kasun Herat and today with me I have Mr. Ashen Fernando. He is a senior electronic engineer at Zone 24/7 Private Limited. And Mr. Ashen is a professional with more than 4 years industry experience in electronic engineering. Also, he is a visiting lecturer at University of Sri Javadnapura, Faculty of Engineering, and he is specialized in embedded system architecture, firmware development, and circuit design with EK2. So, hello, Mr. Ashen. Welcome to Tech Innovator Podcast. It's an honor to have you with us today.
Thank you, Kasun, for that wonderful introduction. And I am very glad to help and enlighten you on some aspects of embedded systems.
So, let's move on to the topic of this episode. It's about embedded system development process. Embedded systems are everywhere, from our cars, homes, our smartphones, medical devices. There's a brain behind the many of products and services we are used on every day. But developing embedded systems can be challenging. There's a lot of factors to consider, such as hardware selection, real-time requirement, and safety concerns. In this episode, we are going to walk you through the embedded system development process step by step, and we will also share some tips and advice how to avoid common mistakes and develop high-quality embedded systems. So, Mr. Ashen, my first question, can you give a brief overview of the embedded system development process?
Yes, Kasun. Now, this is an introduction to a broader topic of embedded systems, and the design process is something that is very important. Developing a product is not a very simple thing. There are steps that we need to follow step by step to come to a final product that we can mass produce. So first of all, we start with something called the proof of concept, which is the initial design. Now, many of us undergraduates think that the POC, the proof of concept, is a final marketable product, but actually it's not. It is actually a test bed which is used to prove that your concept or your idea is workable. But there are few steps that you need to follow afterwards in order to make this product marketable or mass manufactured. So after the POC or the proof of concept, there is a stage called electrical verification stage, which at this stage, we make sure the electrical components, the circuitry, the sensors and everything are perfect. After that comes a stage called design verification. Now, when you look at a product, any product should be designed well, considering the user experience, user interfaces, and things like that. And it should be pleasing to the eye. So these factors are considered in the design verification stage. Then comes the production verification stage. Now, in a production verification stage, what we are looking at is making sure the product you're designing is mass producible, meaning this product should be able to work on a production line. In a production line, there are many things that we need to consider, from assembly to parts available and so much more considerations. So once the PVT stage, the production verification stage, is completed, then we can move on to mass production. So once mass production is approved, we can say this is finally a mass producible product. So many of us think that a proof of concept is a product that can be marketable in the field of marketable to customers, but until a product moves to the mass producible stage, it is not a final product. So these are the main steps we follow when we are developing an embedded system.
Thank you, Mr. Ashen. As a mechatronic engineer undergraduate myself, I find your explanation immensely valuable. As a following up question, Mr. Ashen, may I ask you, what are the key challenges and considerations at each stage of the process?
Yes, Kasun, that indeed is a very interesting question. Now, things that we forget is we sometimes try to mix up each of these stages and sometimes we try to skip these stages. Now, if we look at the proof of concept, in this proof of concept, only engineering team is there. Mostly the design is there. For example, if I have an idea and I want to prove this concept, then mostly myself, I will be working on this proof of concept. I will get components which are off the shelf readily available components and off the shelf development tools. So we are not taking the microcontroller itself, but we are using development boards. And then we are using wires like development kits like Arduino kits or PIC kits or things like that, which are off the shelf available to prove that the concept works. Even when we are getting sensors for this stage, we are getting sensors as modular components. We are not embedding them in a PC. So sometimes we try to confuse this with the electronic verification stage. Now, once we come to the electronic verification stage, which is the second stage, there we have to make sure that your circuitry is fine. So basically, we are moving on to developing a PCB, a printed circuit board. Here we have one board, maybe one motherboard and many daughter boards and sister boards if required, connected by ribbon cables or any other means or even wireless. But our electronic component has to be finalized. So this stage, we won't be using any microcontrollers, but we will use the microprocessor on the PCB itself. And we are not using any modular components. We are using the sensors and the ICs directly on the board. So here we have to, when we are moving to the electrical verification stage, we have to make sure that there are no electronic errors in it. The sensors should be properly working. We have to choose the correct sensors. We have to choose the correct cables. We have to choose the correct indicators, the LEDs, the correct push buttons. And so much has to be verified to come to the electronic stage. Now, once the electronic stage is done, we have your PCB, we have the working component as a PCB. Now the design stage, where we check for user interfaces and user testing. So when the DVT stage or design verification stage is there, we not only get the product to be used by engineers, but most of our products, if we design a product, it won't only be used by engineers, right? It will be used by a customer, a non-technical person, an average person. So we get this product test by an average person to see what their feedback is. Because when we look at things in the engineer's perspective, sometimes we notice we have missed things that a normal user would feel like. For example, if we design a keypad, we press the buttons, but when a user presses the button, he might find it very confusing. Or if there's a specific place to scan a barcode, for example, and we have not properly directed a first-time user to where to hold the barcode to, a first-time user might be confused. I'm sure you might have come across products that are properly not labeled or proper directions to use are not there. So these things should not happen in the DVT stage. In the DVT stage, what we do is to make sure any user, the final user who will be using it, will be using this product without any issues, and we get the feedback from the users. We do user testing, user interactive testing, and then we do the changes required. So mostly this is the aesthetics of the device. Make it look nice, make it look pleasing to the customer and any other user, right? The color combinations, the colors of the LEDs. How are we indicating low battery, for example? How are we indicating an error stage? Things like that. So these are things we consider in the DVT stage. Next comes the production verification stage. Now, in the production verification stage, what we mainly do is make sure this product is mass manufacturable or assembly line suitable, right? So if we design a product, for example, which cannot be used in an assembly line, for example, we are designing a specific device which has a battery, and the battery goes in first and then the PCB. But have we ever thought about replacing the battery? Have we ever thought about repairing? Have we ever thought about the number of screws we are going to use to fasten the product? So if we use more screws to fasten, for example, this product, then the assembly line is going to be long. There's going to be more parts required. It's going to be complicated. But is there other locking mechanisms we can use? What kind of batteries we are going to use? And what are the alternative components? For example, as engineers, we know we are in an economical crisis of some sort with COVID. And China, manufacturing is very less now. And there are components that are there today, and in a couple of months, they might be out of stock. So what are the alternative components that we can give for the specific component, and what if they're out of stock. So these things come to consideration in the production stage, because we are getting ready to mass produce a product, right? And then finally is the mass production stage, where you get this part and get it mass produced, right? And as we go on each of these stages, we cannot make mistakes. Now we can make mistakes in the POC stage, but if we make a mistake in the DVT stage or the PVT stage, then there's going to be a problem, because you have finalized so many things. Mistakes are very costly. And as you go along with each of these stages, there are more stakeholders involved with your product. There'll be a person who is funding your product. There'll be the manufacturers who will be manufacturing your product. There'll be the customer base. There'll be a marketing team. There'll be other teams that are involved in your product. So as you move on these stages, the responsibility of making a change is tough. So that's why each of these stages are important, and the correct things should be checked off at each of these stages. So those are the considerations and challenges in each of these important stages.
Thank you, Mr. Shane. This would be my next question. Can you share some example of the common mistakes avoided in embedded system development process?
Yes, Kasun. Now, as I told you, these steps are very important. Now, there are few mistakes that we as engineers, and sometimes even in the industry, we make mistakes. Right? Sometimes they still happen. So let me mention some common mistakes that happen and how to avoid them. So first of all, we try to leap forward or skip some of these tests. Right? We skip these tests and skip these stages because sometimes the client wants a faster solution. If the solution is they want it fast, then the solution might not be reliable, because the solution might have not gone in each of these specific stages. So if they have missed these stages, then we might have missed the electrical verification, maybe the production verification, so things like that. So it's important we follow all of these stages one by one to avoid any issues. Next, quality control. Now, some of you might have seen when you purchase a mouse or a headphone or any other product of that sort, you might have seen there is a sticker that says QC passed. Now, what does this mean? Quality control. Now, when we are manufacturing something, especially mass manufacturing, it's important to quality control. You have to do quality testing. Whenever you are choosing sensors, considering power supply, quality should be kept. There should be proper ways to measure the quality, and also there should be a consistent quality throughout the product. So that is very important. And also time allocation. Now, when we say there is a product, and sometimes customers want it very fast. Sometimes customers say we want this product in 6 months, but the actual timeline might be 1 year, because research and development takes that time. And if the customer wants it in 6 months, sometimes we might have to compromise on these tests and stages. Now, compromising can come in both ways. Of course, the research cost for the product is going to reduce, but we are also compromising certain tests and some quality. So it's very important that we don't compromise and allocate the proper time for a project. And the proper time should be estimated by a very recognized engineer with experience, so that they know when they see a product or when they see a requirement documentation, they know how long it's going to take to manufacture certain product. Next thing, required standards. Now, sometimes you all might be thinking we only design for Sri Lankan clients. No. Sometimes you might have designed products for international clients. So when you design products for these clients from different countries, we have to make sure that we meet those compliance standards or standardization. Some of you all might have heard things like SLS, ISO. Similarly, even IEEE, there are codes and standards. So Eurocode is one of them, and there are similar standards and compliances each country requires. And there's ROHS compliance, that's for environment, but there are many standards that you have to go, right? And the new standard that is upcoming is lead-free, using lead-free components. That's one example. So certain countries require these standards. So when your customer approaches you, it's very important that we understand these standards and requirements for the specific country or geographical area. So it's very important that we are aware of this before making a product. Next, supply chain management. As I mentioned earlier, the world is currently in somewhat of a silicon crisis, we call it. Because in China, the manufacturing is quite less now due to COVID and the effect. Right now, it's somewhat recovery, but still there are components which are short. Now, as engineers, we have to make sure when we are choosing parts, we find an alternative always. Let's say a specific resistor or a specific operational amplifier, a specific diode is not in stock. We have to always be ready with an alternative to provide for the manufacturers in case they need any additional stock, or in case they want to purchase, and in case the product is out of stock, or in case there is a lead time. So these things are few common mistakes that we always follow.
Thank you, Mr. Ashin. This would be my next question regarding embedded system development process. Even though we follow those kind of measure, there should be more best practice we could follow up mitigate problems that may arise in the future. So can you please tell me what are some of the best practices and tools for the developing embedded system?
Yes, Kashmir. That is a very interesting question. Let me give you some pointers on two of the main segments of embedded systems, which is PCB design as well as firmware development. Now, when it comes to PCB development, there are few main pointers that you need to remember. First of all, you need to plan and document. You can't just start on a PC. When you are doing your schematics, before that, you need to plan what you're going to include and document. Use mind maps, have lists of components, list of requirements before even starting on the schematic. Next important thing is check for proper guidelines and design standards. As I mentioned earlier, when you're designing a product for international standards, there are international compliance rules and codes that you need to adhere to. So when selecting components as well as designing a PCB, it's very important to have these proper guidelines and design standards drawn out. So when you're doing your planning and documentation phase, it's very important to check the proper guidelines and design standards as well. Another thing that is very important, as I have mentioned before, is also to find alternative components. Since there are stock issues, for every component, try to always have a backup component ready, maybe from a different manufacturer, a component that will suit the purpose. So that in case, while you're manufacturing, if there is an issue, if there is a stock issue, you can always refer to the backup components. For the additional components, you have already made the list of additional components you have already made so that they can start manufacturing without an issue. Next important thing is keeping backups. Now, yes, some of you all try to do your design machine and keep it there, but what if there is a sudden issue and you lose your hard disk or you lose your memory? Then what happens? Weeks or if not months of work will be lost. So it's very important you keep backups. I personally recommend to use online cloud backups, reliable cloud backups, either on Drive or Google Drives or OneDrive or any other reliable cloud backup resource. So in case you lose your local laptop at any case, you will always have the cloud backup resource. Next thing, designing for manufacturing. Now, when you come to the PCB layout stage, you should also decide on who is manufacturing your PCBs for. Mostly if it's a PCB manufacturer is in China or there are manufacturers in European countries. So these specific manufacturers have their specifications and rules. Certain manufacturers cannot fabricate PCBs which have certain features. Maybe they have their lowest trace width requirements. Maybe their smallest wire requirements. So those standards, you can get them by talking. For example, the most famous, let me give an example of the most famous PCB designer, which is JLC PCB. So if you talk to them, they will give you like their capabilities. What is the smallest wire size that they can manufacture? What is the smallest trace width that they can manufacture? So from that information, you can make sure your design is better. Now, the other thing is thermal management. Now, when designing a PCB, sometimes we forget that there is a thermal component involved. There are components that are heat up. There are MCUs that are going to heat up. How are you going to manage this thermal component? Are you going to use heat sinks, or are you going to have many power-hungry components close by? Are you going to have a power supply near the MCU? So those things should be avoided when designing. And similarly, another issue is EMI, electromagnetic interference. So we normally don't have inductive components near MCUs because they create electromagnetic waves, electromagnetic interference, and it can actually affect the performance of an MCU. It can affect the flash memory, it can affect memories, it can affect clock cycles, it can affect buses, memory buses. So normally we don't have any electromagnetic interference producing components near microcontrollers or near critical components. So we leave them away, or there are other ways to use shield. So these things has to be considered. And also, most importantly, once you're done with your PCB, review. Even though you designed the PCB, it's always best to get it reviewed by another person, a secondary person, or even a third person. Because sometimes you design, no matter how hard you check for mistakes, you might not be able to find mistakes. But a second person, a third person who's looking at this PCB will be able to find these maybe even silly mistakes. It has happened to me, it has happened to my seniors, it has happened to many other people as well. So no matter how much you're skilled in PCB designing, review is very, very important, because once you manufacture a PCB, unlike a firmware, there is no way you can get it changed without doing any hardware changes. So it's very important to get your PCB reviewed before sending it for manufacture. All right. Let me talk about the secondary aspect, which I was going to talk about, is the firmware aspect. Now, what are the things that you need to consider when you're designing firmware, and the tools and things that good practices you need to follow? Maintaining a good source code, very, very important. I give this message to undergraduates as well. Please maintain a good source code and version control. You can use GitHub, you can use GitLab, or you can use any other version controlling software to make sure that your code is properly in versions, in proper commits, and proper order, so that anyone who looks at knows who has done which changes. Very important. Also, there are coding standards, right? For example, you might have heard variables in camel case, variable in snake case, things like that, right? So there are coding standards that are very important. MISRA coding standard is one of the coding standards, and there are many other coding standards for embedded systems. And it's important that you follow these coding standards. They improve your readability of the code, they improve the standard of the code, they make sure that anyone who looks at the code, it's very readable and easy to understand. So very important to stick to coding standards. Next, maintaining proper documentation. Your flowcharts, your mind maps, your ER diagrams, anything. Documentation is very important so that you know the relationship in your code. Just because there is a code, sometimes it's really hard to understand. And once you're leaving the company or leaving the project, someone has to take over the project. And when they take over the project, there should be some documentation for them to understand what you have done. So very important to code with standards and documentation. Also, next thing is modular design. Sometimes we code in modular designs. For example, you have one sensor, you have it in a separate sheet. In case you want to remove it off, you can remove that sheet off without affecting the rest. So you design the firmware in modular form. The other thing is, make sure your firmware is test-oriented development. There are concepts like unit testing. What we do in unit testing is, while developing the firmware, we write code or small sections that we can use to test the firmware in units, not in bulk, but in units. For example, your code has a small sensor, maybe a pneumatic sensor. You want to just test the sensor, pneumatic sensor only. So there's already a code segment within your entire firmware so that you can test that pneumatic segment. So it's very important you develop your firmware in development called test-oriented development. So your firmware is testable. And the final thing I want to talk about is memory management. Now, yes, sometimes the key thing in developing embedded system firmware is memory management. You have to be efficient when you're declaring memory. How much memory are you allocating? Do you need to allocate mallocs, dynamic memory, or static memory? Or do you need static variables? Or are you using unsigned integer variables? Right? So things like that. Sometimes you can use a unsigned int 8, like an 8-bit variable instead of declaring just an int. Right? So that will save you some set of bits. Sometimes you can, if you need a 64-bit, you can just declare a 64-bit. But if you need 8-bit, you can use a 8-bit. And if you need a Boolean, instead of using an integer for a Boolean application, you can declare a Boolean. So things like that you can use to save memory management in embedded design. So these are the few things. Of course, there is a lot more, but these are the few main factors that I found to share with you for this session.
All right. Thank you very much for your valuable insight of the subject matter. As a closing remark, what advice you would give to someone who new to embedded system development?
Right, Kasun. So this is a thing I've been telling at all of my training sessions and even for my students when I teach. There is so much things on embedded that you can learn, and there is no end to it. There is new technology coming day by day. There is processors with new architectures, lesser values in chip distance. Now there is, when few years ago it was 7 nanometer ICs, and now there are 3 nanometer ICs, and then there is quantum computing. Technology keeps growing, and there is no way that any student or a PhD holder or a professor can learn everything. But there is one that all of you all can learn. That is the ability to learn something and also to keep learning. Because whenever you go to a new job opportunity or a new project, you should learn how to learn. You should learn how to grasp that new project as soon as possible. And when you are allocated to a newer project, even in the same job role, you should have the ability to learn that project in the least amount of time. And that is a skill that you need to develop. And that is a skill that is expected from all undergraduates as well. How you learn to learn. And always, second thing is keep learning. Never stop learning. Sometimes your juniors might know something that you don't. And we have to be humble enough not to learn only from our seniors, only from our bosses, but also to learn from our juniors. There are instances that I have learned from interns who are at my company. So you should be humbled enough to always learn on whatever the opportunity that is available. I think that's the most important and only advice I want to give you, which will cover everything. And you learn and you continue to learn. And the day you stop learning and the day you think that I am done learning, I know everything, that's when you start falling. So that's my message to you. Keep learning.
With that answer, we have reached the end of this episode. Thank you, Mr. Ashin, for joining us today. I'm sure our listeners gained a lot on the topic we have discussed today.
Thank you very much, Kasun, for providing this opportunity. And I would like to thank the IEEE sector as well for selecting me and providing me this opportunity. I wish you all good luck and have a good day.
Thank you, Mr. Ashin. Please rate and review our program if you appreciate it. We have several more episodes planned for you. So stay tuned by following us on the Spotify, Google Podcasts, Apple Podcasts, SoundCloud, Radio Public, Breaker, and YouTube. Thank you for listening, and we will see you in the future episodes.